We're going to go now with some general refresh about processors. And I would like to start by giving you a definition of a microprocessor. So I said a microprocessor handles computational tasks, but how does it do that? A microprocessor will read an instruction of a program that is stored in the memory. It will do that in sequence in order to perform basic arithmetical, logical, or input-output operation. In order to do that, a very successful model that was introduced in 1945 is a von Neumann architecture. In the von Neumann architecture, you have your CPU that consists of a control unit and arithmetic logic unit that is interconnected with an external memory. This memory will contain both instruction and data. So the only thing that your microprocessor does is reading out into the memory to fetch some data or an instruction and is processing that instruction or data. So the main features of the von Neumann architecture, as I said, it is based on the concept of memory stored program. The memory content will be organized, and it will be organized in particular in words, all of the same size. So in our case, we're considering words of 32 bits. And the words in memory follow a linear order based on the address. So we'll start at address 0, then address 32, because you count in terms of bits, and so on and so forth. There are two main memory contents, but no explicit distinction between them. As I told you, both the instruction and data are stored in the memory at the same place. The instruction are program that controls what the microprocessor has to do. So it basically tells the microcontroller what to do in its operation. The data are the pieces of the information that the program will process or generate. So you will basically read instruction that will tell you what to do with your data. And the instruction execution order is sequential. It starts at 0, then goes to 1, 2, 3, and 4, and so on and so forth. Then, of course, you will be able to tolerate jump into the memory based on some instruction. But the bottom line is that you will always do stuff in sequence unless you have a jump operation. In order to know what will be the next instruction you need to follow, you have to look at the program counter. And the program counter will contain the next instruction of interest, the address of the next instruction of interest. If we continue to look at the main features of the von Neumann architecture, we need to look at how a processor deals with the instruction execution. And it typically has 5 phases that are the following. The first step will consist of your processor fetching an instruction. It does look at the address stored in the program counter, goes into the memory location that has this address, read the data that is here, read the instruction that is stored there, and then it will decode the instruction, try to understand what the instruction is about and what the CPU should do. After that, the microprocessor will fetch the operands, insert the operands, so you'll have to go into the memory, read the data, you continue with an execute instruction, you execute your instruction, you will take your decoded instruction and perform the operation on the operands you just got from your memory. And the final step is to write back the results into your memory or register that can be stored in the program. These 5 steps are very important, and they will always be used like that in microcontroller, in von Neumann microprocessors. There are obviously a couple of variations from the baseline von Neumann architecture. And the first one is the instruction set. We are using in this class reduced instruction set architectures that are very popular nowadays, but in the past, people used to create processors with very complex instruction They were called CISC computers, complex instruction set computers. And the idea here was to bridge a semantic gap between very complex operation and between what your processor could do and how complex it was to program them. So you could implement like FFT operation directly instead of just running a program that will do all the atomic steps one after the other. What we're using right now, as I told you, is a reduced instruction set computer where we only have simple instruction, and that allows you to have fast execution of each instruction. That is very useful, for example, to implement low-power processors today. Another alternative is to use the Harvard architecture that instead of the basic phenomenon that does have a memory that contains both program and data informations, the Harvard architecture will have two separate memory buses, one for the instruction and one for data. That will provide you better bandwidth, and it's a very commonly used architecture in digital signal processor DSP, such as Blackfins or some advanced ARM, where you do have this kind of arithmetic operation that hard.